Hello AP Physics 1 students. This video is going to lead you through problem 16 in our packet of rotational dynamics problems. It's a problem that is well worth our time. We're just not going to have class time to do it. So if you'd like to follow through, read the problem, try it, look at the solution, I think it's a really good idea. Alright, so just take a minute to read the problem, get a sense of what's happening, pause the video, and come back. Okay, so here we're looking at a collision problem. It's a collision in a rotational sense. In some sense, it's very much like the child jumping on the carousel where one object connects with the other. And so in a linear sense, that would be one object colliding with the other and then moving off together as a single object. Here, they're going to rotate together as a single object. So we're dropping an identical disk on top of the one that's already rotating. So clearly it's a conservation of angular momentum sort of problem because there is internal torques that allow the bottom one to sort of get the top one to speed up to join it. So we start with the statement of conservation of angular momentum. We can do L1 plus L2. I'm going to write it as equal to L prime because they are combining here in this sort of perfectly inelastic rotational collision. I guess you could write it as L1 prime as L2 prime, except it's really just one object. In the end, though, L2, if that's the angular momentum for this object that's being dropped, it's not moving to begin with, so really it just sort of reduces to L equals L prime. And in that case, it's very similar to the figure skater problem. So which equation should we use for angular momentum? Well, these are clearly not point objects, so we're looking at I omega. So let's say I omega equals I prime omega prime. And again, this looks very much like the figure skater problem. And then we look up, there's a disk, and so angular momentum, of course, for a disk is 1/2 mr squared. Here we're solving for omega prime as I times omega. Here's the original angular moment of inertia of the original disk that's rotating. Here, since the doubles, right, it's just 2 times that. Now, honestly, everything just cancels and we get that omega prime equals 1/2 omega. Although you really should have suspected that. This is very much like one object at rest, another object with the exact same mass coming in, colliding and sticking to it. And of course, since they have to share the momentum, if the mass got doubled, the velocity would be cut in half. So that's what's happening here, right? Since they're identical objects, the moment of inertia gets doubled. And so literally just the angular velocity gets cut in half. You should have suspected it anyway, but here the algebra proves it. Now if you read carefully, hopefully you didn't just go on to part A, we were trying to find two things, right? We were trying to find the final angular speed and the change in kinetic energy. I hope you did not miss that. So, want to find the change in kinetic energy. First thing you want to do is find the initial kinetic energy in the system. What's the equation for kinetic energy? That's 1/2 I omega squared. It's rotational kinetic energy. So you just start substituting the values here. I, again, is 1/2 mr squared. I'm using parentheses here just so we can see here's the half from the equation. Here's the 1/2 mr squared from I. And here's the omega squared. Just want to combine some things. A half times a half is a quarter. So a quarter m1r1 squared omega squared. I want to do the same thing in the final situation. Now I might express it as I prime and omega prime. You notice I'm using parentheses around the omega prime. I think it's a really good idea to do that because if you don't use parentheses, you'll have the prime right next to the 2. It will actually look like omega to the 12th power if you're really not careful. And, you never know what happens on a test when you're rushing and, your handwriting's not as good. You never know what silly mistakes you might make. So just, use parentheses. It's a really good idea to separate that out. It's omega prime squared. What's I prime? Well, remember, it is this. It's twice 1/2 mr squared, and the 2 and the half are just going to cancel. Don't forget this omega prime. That's the 1/2 omega we found back in the previous part. So here's the new moment of inertia, right? Double 1/2 mr squared. The 2's cancel. Here's the new angular speed from before. Put it all together. Take constants out to the outside. And we're going to get 1/8 m1r1 squared omega squared, right? This has to get squared, so a 1/2 squared is a 4th, times a 1/2 is an 1/8. There's the 1/8. We want to find the difference, because of course it's delta, KER, and of course that's final minus initial, always in that order, always, always. And here's just a matter of this minus this. Notice that I've pulled all the constants to the outside, so it's just some multiple of m1r1 squared omega squared. Literally it's 1/8 minus a quarter. 1/8 minus a quarter is a negative 1/8. And so there it is, negative 1/8 m1r1 squared omega squared. Yeah, it's kind of unwieldy with all the subscripts, but certainly not a difficult problem. Part B is a little more complicated, so go ahead and read part B and give it a shot. So here, the second disk is literally half the size of the original disk, and so it has half the mass and half the radius. It's just going to be the same problem again, just, it's not going to be as nice math. So try it on your own and see what you can get. You should be able to get that omega prime is 8/9 the original angular speed. So be really careful with all your factors, where there's a half, where something gets squared. And then when you do your change in kinetic energy, it should lose we should have a change in negative 1/36 and 1 R1 squared omega squared. Again, it's just a little bit nastier math. Just have to be really, really careful. I would suggest using parentheses around every different term there, what the moment of inertia is, what the new moment of inertia is, what the omega is, what the new omega is. I think it's just a good idea so you can visualize it yourself and just keep real careful track of all the factors there.